Okay, so we've done all this review of our integers, and we've talked about variables and powers and all that stuff. We're going to step back a little bit, get rid of the variables for a minute, and we're going to talk about our number systems and tie a few things together. We've talked about our place values quite a bit, and we're going to talk about them even more right now. We've talked about how, this is the ones place, the tens place, hundreds place, 1,000s and 10,000s and so on. And we've mentioned that these are just powers of 10. This is 10 to the 0. Anything to the power of 0 is 1. Very good. 10 to the 1, of course, is the tens. 10 to the second is hundreds. 10 to the third is 1,000. 10 to the fourth is 10,000. 10 to the fifth is 100,000. And 10 to the sixth, and so on. We even talked about how in algebraic numbers, it's not 10 to the power, it's x to the power, and that we can have different number bases. Octal numbers would be 8 to the whatever power to make the place values. Going this direction, it's 10 to the negative 1, which is just 1/10. 10 to the negative 2, which is 1 over 100. Put in my negative there. 10 to the negative 3, which is 1 over 1,000. And you'll notice the negative powers are just the reciprocal of the positive powers. 10 to the third is 1,000. 10 to the negative third is 1 over 1,000, or the reciprocal of 1,000. So 10 to the negative 4 and 10 to the negative 5 and so on, going in that direction. Now when we write numbers, let's say we put in something like this, 3,900,000. A lot of times, to shorten it up, we would abbreviate that. Instead of saying 3,900,000, we might say 3.9 million. But we can see now with our place values written like this, there's another way that can be written. Instead of million, we could just do 10 to the sixth is the millions place. And some of you might be recognizing that as scientific notation. And that's all that scientific notation is naming the first digit, the first non-zero digit. Naming its place value is the power of 10, and then putting the decimal point after that digit. So for example, we could have 0.0092. The first non-zero digit is the 9, right? So everything else is going to go after a decimal point. It's going to be 9 and then the 0.2. And what place value is the 9 in? 10 to the negative third. Yeah, there's a lot of science in this one. So then 47,000 would be 4.7. And the 4 is in the 10 to the fourth, so 10 to the fourth. Now, we don't want to have to write out the place values like this to convert numbers from scientific notation to standard. But knowing that this is how it works helps us figure out what direction to move decimal points and stuff like that. So if I have my 5,800,000 or something like that again, we know that's going to be 5.8 times 10 to the sixth. But how could we get there? Well, right now, because we're going to change it to 5.8, because we want one digit, exactly one digit in front of the decimal point, and it cannot be a 0. Right now, our decimal point's right here. We want it to be here, which would be there. It has to move 1, 2, 3, 4, 5, 6 places. So this is 10 to the sixth. Be careful, however. Of course, here, we want the decimal point to end up where? After the 9, so between the 9 and the 4, 9.4. We want it to go there. It starts here. It goes 1, 2, 3, 4, 5, but this is not going to be 10 to the fifth. It's going to be 10 to the negative fifth. Because this side of the decimal point is the negative powered place values up here. They're not negative place values, but they're negative powers because they're small. Basically, really small numbers, of course, are in the negatives, in the negative place values, negative powered place values, and the big numbers are in the positive powered place values. So we can convert back and forth rather easily. To the negative power. You can only have one digit in front of the decimal point. Okay. But we will get into something called engineering notation, which will have something like that in it. So what's this one going to become? 4.2, 3, 6, 7, 8. And this one. 3, 4. Negative 4. How about this one? What's this negative out in front do? Nothing. Absolutely nothing. It's still going to be 7.3 times 10 to the, starting here, moving to here. How many places does it move? 1, 2, 3, 4, 5. So negative 5 or positive 5? Positive 5, because that's a big number. And that negative just goes back in front. It's a negative number. Negative does not affect the place values of the powers. It's just a negative number. So how about this one? Okay, 2.7, and then it is, 3, 6, 7, negative 7. And then the negative goes in front again. Not so bad. So what if I give you, and actually convert that into standard or decimal notation? What are you going to do? Okay, the 5 is saying we got to move the decimal 5 spots. The negative is saying we got to make this a smaller number. So 1, 2, got to fill in 0, 3, 4, 5. So 0.00048. Now, for those of you who are wondering if I'm doing it intentionally, yes, I am intentionally leaving that space every 3 decimal places. Something to get used to. Even in bigger numbers, I still write my commas like this, but big companies are changing over to not using commas like that at the thousands and the millions. In some other countries, they don't use decimal points. They use a comma in place of the decimal point. So they don't use commas anywhere else, so it's not confusing. So they just use that extra half space when we get to where the comma would be for our system.
So metric numbers not use commas too?
Metric numbers avoid commas, they just use the space. Yeah, because it's a European system. And yeah, in Europe they don't use the comma anymore.
So do they use decimal or comma then?
That depends on where you're at.
Okay.
So anyway, how about this one? It's got to move 5 places, and this is a positive, so we're going to make the number bigger. So yeah, we're going to go 1, then 2 at a 0, 3, 4, 5. So 280,000. What do you think? Better than sharp stick in the eye? I want you to try a couple for me here. Convert those two into scientific notation. And convert those two into standard notation. Okay, so what's this one become? 2.9 times 10 to the 9th. Good. And this one? Perfect. Negative 8.3 times 10 to the negative 4. This one. 0047. Good. And this one. Negative 3,700,000. Perfect. Well, there is something called engineering notation. Now, engineering notation has a place. We said that scientific notation can only have one digit. It must have exactly one digit, and it can't be a 0 in front of our decimal point. Well, engineering notation loosens up on that a little bit. Engineering notation can have anywhere from 1 to 3 digits in front of the decimal point. But it's the power of 10 that's restricted. The power on the 10 must be a multiple of 3. So 0, 3, 6, 9, 12, or negative 3, negative 6, negative 9, and so on. So if I have $47 million and I'm going in engineering notation, I must move the decimal point 3 spots at a time. So I go 1, 2, 3. Can I go another 3? Yeah. 4, 5, 6. Can I go another 3? No. So that's just 47, and I moved it 6 spots times 10 to the 6th. Not so bad.
Not so bad, but why would you want to do that?
We'll get to that. Give me a couple seconds. How about this one? Can I move my decimal point 3 spots? You bet. 1, 2, 3. Can I move it 3 more? First instinct to say no. Guess what? You have to. Why do we have to? Yeah, right now there's nothing in front of the decimal point except zeros. There has to be between 1 and 3 digits. So I have to go 4, 5, 6, and add a 0. That's 590 times 10 to the negative 6. So the question's been put out there, and I promised an answer. Why would we want to do that? Why? Well, because the 3 is a big deal. Why is it a big deal? Well, this looks familiar? Our metric system. We said the deci and centi don't get used a whole lot. And the deca and hecto don't get used a whole lot. What gets used, meters itself is just 1 meter, that's 10 to the 0. A millimeter is 1/1000, that's 10 to the negative 3. Micrometer is 1/millionth, that's 10 to the negative 6. Nano would be 10 to the negative 9. Pico 10 to the negative 12. Femto 10 to the negative 15. Kilo is 1,000, that's 10 to the 3rd. Mega is 1,000,000, that's 10 to the 6th. Giga would be 10 to the 9th. Tera 10 to the 12th. And so on. Now, we do have the units in between here for length and stuff, some of that stuff. But if we were talking about electricity, this would be volt, millivolt, microvolt, volt, and kilovolt, and megavolt. We don't use decivolts and centivolts or amps and ohms and stuff like that. There's a lot of things where we don't use those in-between ones. These ones that are every third power of 10 get used a lot. So now when we're doing calculations in the metric system, one formula that we have is the volts are equal to current times resistance. I stands for current in amps. R is your resistance in ohms. So if we have a current of 25 milliamps and a resistance of 1.2 mega ohms. That upside down looking horseshoe type thing is the symbol for ohm. It's the Greek letter omega. What I'm going to be doing here is 25 microamps times 1.2 mega ohms. This is really 25. Micro is 10 to the -6 amps times 1.2 mega is 10 to the +6 ohms. Our metric prefixes are engineering notation. So when we look at doing operations in engineering notation, it's our metric prefixes that we're really operating with. Does that make sense? So speaking of operations, quick little review. What's 7x plus 2y? Yeah, 7x plus 2y. Why? Because when we add or subtract, we must have the same name. We cannot combine those as just 7x plus 2y. But if it were 7x plus 4x, now we can combine them. Combining the count, 7 plus 4 is 11, and we keep the same name, x. When we were talking about whole numbers, the same thing applied, but the name was hidden in the place values. Each digit had a name, its place value. So if I'm looking at a number in scientific notation, like 4.2 times 10 to the 7th, what part of that is implying a place value? 10 to the 7th. So the 10 to the 7th is the name. The power of 10 is our name. The 4.2 is the count. So when I'm doing operations with numbers in scientific notation, it's going to behave the exact same way as any other number. It's just those are the two parts. Those are the count and the name that we have to work with. And just like fractions, decimals, and other things, it looks a little different because it's a little bit different form of a number. So let's take something like 3.4 times 10 to the 9 plus 2.7 times 10 to the 9. Can I add those? Do they have the same name? Yeah, they're both 10 to the 9th. What am I going to do to add them? Well, I always, when I add, I combine the counts. 3.4 and 2.7 make 6.1, and I keep the same name. Exact same rules as any other form of numbers. Can I add those? Sure can. What do I get when I add them? Well, I combine the counts. 1.8 plus 5.7 is 7.5 times 10 to the negative 13th. I keep the same name. Now, you guys know me well enough by now that I don't stay with the simple parts, right? It always gets worse. 6.4 times 10 to the 7th plus 5.3 times 10 to the 7th. You might be looking at it saying, that don't look so much worse. What's 6.4 plus 5.3? 11.7. We combine the counts times 10 to the 7th. But this time we're not done. What is wrong with that right now? There it is. We've got two decimal places, two digits in front of the decimal place. Move the decimal point over, make it 1.17. Did the count get bigger or smaller? It got smaller, so the name has to get bigger. 7 plus 1 is 8. Every time you move the decimal point, it's multiplying or dividing by 10, right? We made this number smaller by a 10. That 10 has to go on our power. Number gets smaller, power gets bigger. Number gets bigger, power gets smaller. Basically, you can look at this as 1.17 times 10 is 11.7. So we took this 10 out of the 11.7 and combined it with the 10 to the 7th to make 10 to the 8th. Does that make sense? That's the long way about it.
But the 7 is considered a significant digit because we started with it in this?
Yes. Yeah. Yeah, because it's not, because in scientific notation, the location in that count is not really a place value. The place value goes to the power of 10.
I just remember a lot of times we drop the 7 to 10. So it's,
Oh, sure. So you only have in one decimal place. As long as you're adjusting the power of 10, it's still in the right place value when you're adding or subtracting. If you're multiplying or dividing, then it gets trickier. Then you, a lot of times you do have to drop it.
that's because you sensitive with your equipment to measure.
Yes,
You only keep to the number of significant digits you can measure.
exactly. In your notes, I want you to try this one. So 7.8 plus 4.4 is 12.2 times 10 to the negative 9. But of course, there's a little bit of an issue here. There's 2 digits in front of the decimal point. So it's going to become 1.22. Now the number got smaller, power gets bigger. What is negative 9 plus 1? Negative 8. Negative power. So adding 1 to it, negative 9 goes up to negative 8. That's why I always do the adding one. Instead of just saying making it bigger by 1 or smaller by 1, I always do the plus 1. So that way it's a little easier to make it work. So now what if they don't have the same power of 10? What if I have 3.49 times 10 to the 7th plus 9.6 times 10 to the 6th? Well, I have to change them just like fractions or anything else. I have to change their name to give them the same name. Usually if I'm adding, I would normally go to the larger power of 10. So 3.49 times 10 to the 7th will not change. This one, however, is going to become times 10 to the 7th. Now we got to go the other way. The power got larger by 1, so the number has to get smaller by 1 place value. So this is now 0.96. Power gets larger, number gets smaller. Now we can go ahead and add 3.49 plus 0.96 is 4.45 times 10 to the 7th. And that is in good form, so we can leave it just like that. Subtraction. Subtraction's a breeze once you can do addition. Just like addition, you have to have the same name. And just like addition, you combine the counts. What's 7.3 minus 5.1? Careful. 2.2 times 10 to the 13th. (6.4) times 10 to the negative 9th minus 2.3 times 10 to the negative 9th. Combine the counts with 6.4 minus 2.3. 4.1 times 10 to the negative 9th. We can run into this issue. What's that? Oh, I'm sorry. Is that better?
And up on 2 problems up, like how did you put 0 in front of the decimal?
Here?
Yeah.
I just had to move it over 1, right? So it's 0.96. I just put the 0 there for form. The 0.
How can you put, you said there has to be 1.
Yeah, this is improper scientific notation, but it's not my result.
Okay.
You know, you can have it in the process of working with it, you can have numbers that are in proper form. Like this was improper form, so we changed it. But in the process of working the problem, we had to go through that improper form. The same here, you're right, this is improper form. That's not proper scientific notation. But we had to go through that form so that we can combine these two numbers.
You can just plug in the signs of your calculator without shifting, can't you?
Yes, the calculator will adjust it for you. So let's take 7.4 times 10 to the 15th minus 8.7 times 10 to the 14th. So again, we could go to the higher power. We could go to the lower power if we wanted to. We just may have to adjust powers later. Either way, we might have to adjust powers later. So this is going to say 7.41 times 10 to the 15th. We're not going to change that. This one, however, is going to change to 10 to the 15th. So the power got larger, the number has to get smaller. So 0.87. So 0.87 now. So we're going to subtract. 7.41 minus 0.87 is 6.54 times 10 to the 15th. So in your notes, try to do that one. So we're going to have to change the powers. Which power are we going to go to? Which one's bigger? Negative 7 is bigger. No, it doesn't. In this case, actually, it would end up being easier to go to the negative 8. So let's do that. 2.89 times 10 to the negative 8. We're going to leave that one the same. This one we're going to change to 10 to the negative 8. Did the power get bigger or smaller? From negative 7 to negative 8 is getting smaller. So the number gets larger by a decimal place. So 37.5. So now we go ahead and subtract. What are you going to get? 37.5 minus 2.89 is 30. 34.61 times 10 to the negative 8. Now we can't leave it that way. 3.461 times 10 to the... This gets smaller, power gets bigger. Negative 8 plus 1 is negative 7. So you just have to adjust later. So, when we multiply, did we need the same names? No. 4x times 7y? We can do that. 4 times, we combine the counts. 4 times 7 is 28. But then we also combine the names. X times y is xy. So when we get into scientific notation, we do not need the same name. 10 to the 9th and 10 to the 5th, no problem. We're going to combine the counts. 4.2 times 2.1 is, what's that? Careful. Times. 8.84. 8.2. 8.82. But then we're also going to combine the names. What's 10 to the 9th times 10 to the 5th? 10 to the 14th. When you're multiplying powers of 10, you add the powers. So this one, we're going to multiply the counts. What's 7.3 times 3.8? 27.74. And then we're going to combine the powers of 10s. We're going to multiply the names. 10 to the 5th times 10 to the 11th. 10 to the 16th. Of course, we're not done yet. Got to move that over. This is 2.774. Now, here's where in science you'd probably round that 2.7 or 2.8. Because there's only 2 digits here. You only put 2 digits there. Times 10 to the 17th. The number got smaller, power gets bigger. Yeah, for the most part. In mechanical design, you would. So that would be the rules you would follow.
What about double zero?
It all depends on the situation. So here, 4.9 times 7.1. 34 point what? 79 times 10 to the negative 3 times 10 to the negative 12. Well, what's negative 3 plus negative 12? Negative 15, right? But we got to move that decimal point. 3.479 times 10 to the plus 1 is negative 14. Not bad at all. Where it can be a little bit confusing is when you mix positive and even powers, like 3.8 times 10 to the 13th times 4.6 times 10 to the negative 8th. Well, first of all, 3.8 times 4.6 is 17.48 times 10 to the 13th times 10 to the negative 8. 13 plus negative 8 is 5. Then we move our decimal point, 1.748 times 10 to the 6th. We can divide. Not near as bad as it looks. We're going to divide the counts. 1.728 divided by 1.2 is 1.44. 10 to the 13th divided by 10 to the 8th. We subtract. 13 minus 8 is 5, so 10 to the 5th. And that's all we got to do there. But we can run into ones like, gotta be careful here. Something like this. 2.1 divided by 1.5 is 1.4. 10 to the 7th divided by 10 to the 12th. 7 minus 12 is negative 5. So you can have the negative powers in there. And it can be really kind of nasty when we do this.
Yeah, you put the negative power because you subtracted the power.
Yeah, 7 minus 12. Yep. When you're dividing powers of 10, you subtract the powers. You okay? You sure? How about this one? 3.2 divided by 2.0. 1.6 times negative 4 minus a negative 9. Negative 4 minus a negative 9 becomes negative 4 plus a positive 9, or positive 5. You look confused. Okay. You're no longer confused, or you no longer look confused? You don't sound so sure. You good?
Yeah, I got it.
Okay. Okay, so we have 2.2 times 10 to the 9th divided by 3.6 times 10 to the 4th. I don't know why I'm stuck on 10 to the 5th in my answer, but that's okay. We're going to divide 3.2 divided by 3.6. 0.888, we're going to go 0.889. Times 10 to the 5th. 9 minus 4 is 5. But we can't leave it like that. Right now there's just a 0, so we've got to move it over. So 8.89 Probably actually we just round it to 8.9 if we were doing significant digits, but we're not going to worry about that right now.
If I'm doing a test without thinking about it.
That's fine. That would be fine. So 8.89 or 8.9, but the number now got larger, so the power gets smaller. So 5 minus 1 is 4, 10 to the 4th. Make sense? Well, then back to that example from earlier. Voltage equals current times resistance. And I might use different numbers a little bit here. Let's say the current is, now let's go with 12. Let's go microamps. And the resistance is 4.5 kilo ohms. So my voltage, my current, again, 12 micro is 10 to the negative 6 amps. Times my resistance, 4.5 kilo is 10 to the 3rd ohms. And 12 times 4, well, how can I have 12? Can I, well, I thought I could only have one digit. This is engineering notation, not scientific. 12 times 4.5 is 54. 10 to the negative 6 times 10 to the 3rd. Well, negative 6 plus 3. Negative 3. An amp times an ohm times an ohm, I wouldn't expect you to know that, but electronics, that's a volt.
It's got the wrong numbers.
Yeah, this is bad etiquette. If you're in research grade physics or chemistry, your errors can build up to the point where your errors are bigger than your answer, so your answer is irrelevant. Yeah.
How do you know if it's scientific or?
It'll tell you. Or if it's just in, if it's in metric prefixes, then you're going to be using engineering notation. So 10 to the negative 3 is milli, so this is 54 millivolts. I think it's time for you guys to practice some, see how this goes. In your book, there's a few pages here. We'll get a little work time in the second hour, don't worry. Page 204, exercise 612A. This is the big book, by the way. 205, sorry. I wrote 205 and said 204. Also on page 205, it's exercise 6-12B. I'm tired this morning, so I'm off. Have I ever told you guys I am dyslexic? Yeah. So yeah, when I get tired, some really strange things. I'll write something. Last night I was tired. I kept saying 6 and writing 2. And 6 is what I really meant. But every time I said 6, I wrote down 2. That class was all sorts of screwed up before I was there. How did you subtract 8 minus 2 and get 2? Why didn't I got 6? Oh, I wrote a 2, didn't I? Sorry. On page 208, it's exercise 6-12C. Couldn't see that coming. Yep. On page 281, exercise 9-1, 7A. On page 282, exercise 9-17B. On page 283, 17C.
Maybe it did mean something else. Come on now.